2. Direction of induced EMF and current. Before we further investigate the Faraday's law of electromagnetic induction, we should better master Lenz's law, which is a simple law to find the direction of the induced EMF. A. Lenz's law. We know the relative motion between a magnet and a coil may induce an EMF, and hence a current. Let's look at the following cases. There's a bar magnet moving from left to right, with its north pole pointing right and moving into the solenoid. According to Lenz's law, there will be an induced north pole at this end of the solenoid, which may then repel the incoming magnet and try to stop its motion. As the induced current flows and produces a magnetic field, the magnet is repelled. Hence, the motion of the magnet is decelerated by the repulsion, and the kinetic energy of the magnet is converted to electrical energy as the current flows in the circuit. Yes, this is the simplest design of a dynamo. Mechanical energy is converted to electrical energy. You may wonder why not a south pole is induced, and of course, it cannot be a south pole. Otherwise, the magnet is attracted and accelerated, and there will also be electrical energy generated in the circuit. So does it make sense when both the kinetic energy and electrical energy are generated without a source of supply of energy? And of course not. Lenz's law says that the induced current should be in such a direction to oppose the change that induced the current. Sounds complicated, right? Let's see how we applied it in the following case. In the next picture, the north pole of the magnet is moved away from the solenoid. According to Lenz's law, the induced current should be in such a direction to stop the magnet's motion. So the solenoid should try to attract the receding magnet, and hence a south pole is induced, as shown. In these two cases, there is energy conservation. In both cases, we have the kinetic energy of the magnet to be converted to electrical energy in the circuit. While the magnet is being repelled or attracted in the second case, work has to be done on the magnet so that the magnet decelerates. The work done on the magnet is negative, and that will produce electrical energy in the circuit. Lastly, let me remind you about the connection of the galvanometer. When current flows in to the galvanometer from the red terminal, which is also called the positive terminal, then there will be a positive reading. On the other hand, when current flows out from the positive terminal, which is colored red, there will be a negative reading. B. Fleming's right-hand rule. To handle problems about a moving wire inside a magnetic field, we usually use Fleming's right-hand rule instead of the Lenz's law. The application is similar to left-hand rule. But please remember that left-hand rule finds induced force while right-hand rule finds induced current. Let's see how to apply right-hand rule in the following example. Example 1. Determining the direction of induced current. A rectangular coil enters a region of magnetic field as shown. First, we apply Lenz's law to the whole coil. We see that the coil experiences an increasing magnetic field pointing downward. Hence, there should be an induced current that can produce upward magnetic field, and therefore the induced current flows in anti-clockwise direction from A to B to C to D. Second, we apply right-hand rule. We may apply the rule on AB, and we will easily find induced current flows from A to B. So the current in the coil flows anti-clockwise again, and AB works like a source in the closed circuit, where B has a higher potential, like a positive terminal of a battery, as current flows out from B. Well, you may also apply that on CD, and find the induced current flows from D to C also. But this induced current is smaller since CD is further away from the magnetic field. Thus, the induced current flows anticlockwise eventually. Moreover, as the induced current flows inside a magnetic field, there will be an induced magnetic force, as we have learned in the last chapter. Let's consider AB and verify that the force is pointing to the left. The induced current flows from A to B. We may now apply left-hand rule. Left-hand rule. And you will find an induced magnetic force to the left, and this is an induced magnetic force due to the induced current flow. The magnetic force directs left, and hence this force decelerates the coil. In terms of energy, the kinetic energy of the coil is converted to electrical energy in the circuit, as the coil tries to move into the magnetic field. The situation can be more complicated if the magnetic field is not uniform, but increasing, for example. Example 2. Current induced in a coil. This question is about a bar magnet passing through a solenoid. We usually use Lenz's law to handle the situation. So in this question, a bar magnet moves from right to left through a solenoid. It is divided into 3 stages. First, the North Pole enters the solenoid. Then the magnet is totally inside the solenoid. And lastly, the magnet emerges from the left and leaves the solenoid. Lenz's law can quickly give the induced current direction. First, in stage 1, a North Pole is induced to oppose the approaching North Pole of the magnet. Second, there's no induced pole, as the magnet is totally inside, and hence the solenoid can experience no change in magnetic field. Third, the south pole of the bar magnet is leaving the solenoid, and hence a North Pole is induced in order to attract the leaving magnet. Thus, the induced current changes in direction as the bar magnet passes through from one direction to 0 to another. Experiment 5C. Investigating induced EMF in a coil using data logger. A data logger can record the induced EMF in a coil as it falls through a horizontal coil. This is the same situation as in example 2, but the whole setup becomes vertical. Therefore, there will be an induced current in one direction and then becomes 0, and then changes to opposite direction.
We will use the voltage sensor to find out how the induced EMF in a coil is affected by the number of turns of the coil and the speed of the magnet moving towards and away from the coil. Run the data logging program on the computer. Set both the sensitivity and the sample rate of the voltage sensor to high. Display the voltage time graph. Start data recording and drop a bar magnet from a height of 20 centimeters above the coil with the north pole facing downwards. Stop data recording. Observe the voltage time graph plotted in real time. What happens to the induced EMF in the coil when the magnet enters and leaves it? Replace the 20-turn coil to a 40-turn one and obtain another voltage time graph. How does the induced EMF in the coil change with its number of turns? This time, drop the magnet from a higher place so that the falling speed of the magnet will increase. Observe the voltage time graph obtained. How does the induced EMF in the coil change with the speed of the magnet moving towards and away from the coil?
Example 3. Magnet falling through a coil. This example further investigates the experimental result. Depending on the polarity of the magnet and the connections to the coil, we may have another similar result. But for both of them, since it is a vertical motion, the bar magnet accelerates. And so, the current in the second stage has a larger magnitude due to the higher falling speed of the bar magnet. By the way, the magnet does not actually accelerate at 9.81 meters per second square, but a bit slower. In terms of energy, the gravitational potential energy loss of the bar magnet is partly changed to electrical energy in the circuit due to that electromagnetic induction. But still, most potential energy loss becomes kinetic energy of the bar magnet. In terms of forces, the bar magnet experiences a small upward magnetic force when it was entering and also leaving the coil. The free body diagram can explain why its downward acceleration is slightly smaller than g. Example 1. Effect of induced current. This is an 8-level question which deserves special attention. As you can see from the diagram, a rectangular coil is receding and therefore leaving the current-carrying solenoid, which produces a constant magnetic field. As the coil may experience change in magnetic field, there will be electromagnetic induction, and hence induced current flows in the coil. Since the upward magnetic field experienced by the coil becomes weaker and weaker as the coil is receding, the induced EMF should produce an upward magnetic field in order to oppose the change. So, the induced current will flow from E to D to C to F and back to E again. And in this way, the observer P will see an anti-clockwise current. This is the result deduced by using Lenz's law. And now let's check it using left-hand rule to find the forces on the coil. So first, this is the induced current flow from E to D to C to F. Then this is the magnetic fields at CD and EF. You may notice that the magnetic field at EF is weaker because it is further away from the solenoid. Then you may apply the left-hand rule, and you will find the induced force. Due to the stronger magnetic field at CD, there is a larger induced force on CD, and the magnetic force on EF is outward, which is also smaller. So the net force on the coil would be inward towards the solenoid, and in this case decelerating the coil's motion. Similarly, you may also use Feynman's right-hand rule instead of Lenz's law in order to find the induced current direction. However, you will see when you apply that on CD, current flows from D to C. When you apply that on EF, induced current flows from E to F, and they are contradictory again. And since the magnetic field at CD is larger, the induced EMF there is also larger, and so finally the current flows from D to C to F to E, the same result as deduced by the Lenz's law. But of course you will find the Lenz's law simpler to apply. Now do check point 2 below.